just introducing it now. This is the magnitude of the force of gravity, m times g, where this m is mass of the chalk, and g is that ubiquitous 10 meters per second squared, right? I didn't put a minus sign here because I'm representing the length of the vector. There's no subscript y here, and there's no vector over the top sign. So what I mean by this is the length of my vector, and I can rewrite it as mg because I know the law of gravity. The law of gravity near the Earth's surface. This is sort of a provincial law. It's not really a universal law of gravity, but near Earth's surface, the force of gravity on an object is the mass of the object times g, and it points down, right? So there you have it. There's a law of gravity. This is not Newton's second law. This is not Newton's third law either. This is a law of gravity, if you like. It's telling us what the force of gravity is on any given object. If you know its mass, you can say here's what its force is. The fact that it has exactly the same form, F equals m times the acceleration thing, the same form as Newton's second law, is why there's this cancellation where the masses cancel out. But we'll get there in a second. So, all right, so F equals mg, that's the force of gravity acting on the piece of chalk. Now, the chalk, you already told me, what's the acceleration on this chalk? 0. So its acceleration is not g. Students will want to say, oh yeah, the acceleration of the object is g. I know because the force of gravity is mg and gravity's acting on it. But it's not true. It's not accelerating. And that's because gravity's not the only force acting on it. There's another force that I'm calling a normal force. That's a force from my hand onto the chalk. So I could have also labeled it F sub hand or something. But this way, by calling it a normal force, I can also put it on the table and say, all right, it's the same situation. So gravity's acting straight down. The table is pushing up on the chalk. We'll refer to it as a normal force. The reason we call it a normal force is that it points perpendicular to the surface between the chalk and the table. So if you have chalk on my hand and the table, here's the table, right, here's the chalk. The force acts right where they make contact. It's right there. And it points upward. And that's from the table on the chalk, right? So by the way, does the chalk exert a force on the table? Yeah. By whose law? Newton's, which one is it? Newton's third law. So we can write another force up here that's true. So I'm drawing a diagram of situations. All right, let's move this label. You know what this is. This is a table. I can have a force that goes like this too, right? That's the force of the chalk on the table. Now when I write the free body diagram for the chalk, I don't include this force because it's acting on the table. It's not acting on the force. Yeah, what did I say? On the chalk, right? So that's really important. Because this is for Newton's second law. This is a picture here that's sort of depicting what's going on with Newton's third law. These are Newton's third law pair. This is a third law pair of forces. This is the equal and opposite force to this one, right? Chalk on table, table on chalk. But when you do free body diagrams, it's all on the chalk. It's every force in the problem that's acting on the chalk and no other forces. Also, I don't include the net force either. So one thing that students have is they'll put all the forces acting on the chalk and then they'll add the net force on the chalk. But that's double counting, right? But when you say net force, what do you mean? You mean the sum of these forces. In this case, what will the sum of forces be? 0. You know that right off the bat because the chalk's not accelerating, right? It's not accelerating right there. So that means that the net force has to be 0. And it means that if there's a force of gravity that you know is acting on the chalk, then you know there's going to be a normal force that acts the opposite way. You might be bothered, wait a minute, the normal force, how does it know? You know, the size of the normal force depends kind of on how big the force of gravity is. And you can sort of see how that works, right? The chalk is sitting there, and suppose I add some force. Suppose I add some force and push down harder. So now gravity's pushing down the chalk, and I'm pushing down the chalk. I have to modify my free body diagram by adding another vector downward. That's the force from my hand on the chalk. And there's 3 forces acting on it. But the normal force would have to go up to balance out the greater downward force so that there's no net force acting on the chalk. How do you know that's true? Because it's still not accelerating, right? The chalk itself is still not moving around, so the acceleration is still 0. So let's write this out formally with Newton's second law. Newton's second law then says, and let's say in the y direction, and I define my y-axis, because I can write Newton's second law as a vector equation. That means there's a different equation for every dimension in my problem. There's x and y. I got 2 equations. So in the y direction, there's the force of gravity, y component, plus the force of, let's say that I'm not pushing down. We'll do the case where it's just sitting on the table. So there's a normal force, and I want the y component of the normal force, right? And notice it's a plus sign here because these things, this might be, like this is going to be positive. No, this will be negative, right? Because I define my y-axis to be pointing up. This will end up being positive and negative. So there's hidden negative signs here. The convention I use is that when I put a subscript y, I mean the y component of the vector, whatever it is, fg vector, here's the y component of it. Might be negative, but I don't explicitly put a minus sign in here. I've got a subscript that tells me that I want that component. Okay? I mean, use whatever convention you want, but this is what I do to keep myself clear on where the minus signs go. That's so much. It's all about accounting. You know, all right, that's my net force, right? So here's the general equation. I said that F net in the y direction equals m of the chalk, right, times acceleration in the y direction. So that's the general equation. That's the y part of Newton's second law. Here I'm putting particular values in for the forces that are added up to produce the net force, and over here I put, you guessed it, the mass of the chalk times the acceleration in the y direction. In this problem, though, we already know that the acceleration equals 0. So if I wanted to know what's the magnitude of the normal force, I would say, oh, it's going to have to be the same in the opposite direction as the force of gravity. And you already did that in your heads, but this is formally how I do it. And I say, okay, what is that? Okay, it's negative mg, and this is positive f normal y equals 0. Okay, so you guessed it. The normal force, the y component of the normal force is equal to mg. Right? And in fact, because normal, so what do we mean by the normal force? We mean the force, the contact force from the chalk and the table that is perpendicular to the surface. That is in the y direction, so I don't even need to put this on here. The thing that's weird about it is if I have the subscript here, it might change the sign, and if it's not there, it won't. It turns out in this problem, they're the same, right? Because I define my y-axis to point straight out. So, all right. Okay, so that's mostly about conventions keeping your signs straight, but there's physics there too, which is that you have multiple forces in the problem. You have to keep track of where they're acting. Let me ask you this. So there's 2 forces acting on the chalk. Gravity's pointing straight down, normal force from the table is pointing straight up on the chalk. We found the Newton's third law of pairs for the force on the table and the force on the chalk, right? But what about the force of gravity on the chalk? So here's your chalk, here's gravity, right? mg pointing straight down on the chalk. Is there a Newton's third pair? Is there another force that is in opposition to this, acting on something else? What do you think? Yeah, that's the law, right? Gotta be. So what is that force acting on? Like, where does gravity come from? Why is this so? What is it that's exerting a gravitational force on this piece of chalk? Is it me? What is it? What's the nearest planet? Earth. Earth is pulling on this chalk with gravity. Well, the chalk's pulling back, right? It's pulling back with a force that's equal in magnitude but opposite in direction. That means that when I let this chalk go, not only does the chalk accelerate downward due to the force of gravity on the chalk from the Earth accelerates upward due to the force of gravity from the chalk. But how come we don't notice that? How come we all just, when I let go of the chalk, why doesn't the room start, why doesn't it make me feel it? Well, the Earth is more massive, right, than the chalk, by a lot. So that means that if the forces are the same, so Newton's third law relates forces, not accelerations, right? It says that the force from the chalk on the Earth has to equal the force of the Earth on the chalk. But by Newton's second law, we know that the acceleration, the resulting acceleration on an object, goes like 1 over the mass times the force acting on it, right? So that's why. The force that the chalk exerts on the Earth is the same as the force that Earth exerts on the chalk. But the accelerations that result from this are different because the Earth is much more massive than the chalk. Now, we don't really treat gravity in its full proper form in this class because we cover so much in this class as it is. We treat gravity as something that happens near to your surface, and it always points straight down, and it results in acceleration of 10 meters per second squared, or if you like, 9.8 meters per second squared. A more general treatment would deal with objects that can go further away from the Earth, like satellites or other planets or the sun, moon, right? And we can talk about how gravity falls off. The force of gravity falls off whenever r squared, turns out, where r is the distance from the center of the Earth as you go away. But we're not going to worry about that in this class. You will see force laws like that if you take 8b, because then you'll get into electricity and magnetism, and you'll deal with electrostatics where you have these kind of laws. But in this class, we won't deal with that. But I just want to be clear that we're skipping over that stuff. But it's good to think through, like, yeah, the Earth is an object in space that exerts gravitational force and things around it. So is this chalk, you know. And even though we treat them on unequal footing because the Earth is much more massive, and we're not going to deal with places away from the surface of the Earth, we're going to have gravity be fixed at 10 meters per second squared straight down. It's still good to remember that the Earth and the chalk are both, they're the same in the eyes of the law, you know. These laws apply equally well to the Earth as they do to the chalk. And there is always a Newton's third, there's always another pair, I keep saying the wrong way, there's always another force out there to make a Newton's third pair for any force in the problem, even if it doesn't show up in a natural way in the problem. And when you write down Newton's second law and use free body diagram, you're only focusing on forces acting on a given body. So it's not the case. These forces, I already said this, I'll say it again, these two forces do not both show up on the same free body diagram. This force is right here. So one of the forces shows up here, because it's acting on the chalk. The other one shows up on the free body diagram for the Earth. So we can make a free body diagram for the Earth. It'll have this downward force due to the chalk pushing down on it, right, with its normal force, and another force is pushing up on the Earth, or pulling up, if you like, on the Earth, through the gravitational pull toward the chalk on the Earth. So that those two forces would show up on the Earth's free body diagram. All right, enough of that. So there's law of gravity. And let's think about what happens. If you're in an elevator, right, maybe the elevator's being held up with a rope, right? So there's tension in the rope. Rope is pulling. Ropes pull, right? So this exerts a force on the elevator that points which way? Up. Let's say that this guy's holding still. Let's say you're sitting at the third floor and you're not moving. You're not accelerating right now. So A equals 0. Well, there's a force that this rope exerts on the top of the elevator that's upward. On the ground, this guy, he's not accelerating. He's sitting still on the third floor, right? So he's got a downward force of gravity and an upward normal force, just like the chalk did on the table. But now suppose we do a dastardly thing and cut this rope, right? So now what's the tension inside the rope? 0. Yeah. And the elevator starts to accelerate straight down. And this guy now, he's really, he's tipping over. He no longer, and he feels weightless, right? But what does that mean? Is there still a force of gravity acting on him? You bet. He's not weightless. He's just going to hit the ground really hard, right? There's a cushion. All right? He's paid a lot for this. He's weightless, but that just means he's not feeling the normal force pushing up on him from the ground. So in this case, he feels a normal force from the ground that's equal and opposite to the downward force of gravity acting on his body, right? Over here, he's experiencing the force of gravity, but he doesn't notice it because it's acting on all parts of his body, right? So like his feet are being pulled down by gravity, yeah, but so is the top of his head. Now, if you get near a black hole, which none of you are going to do, unless you've got resources beyond what I can imagine to get what those things are, you think they're out there. Actually, we're almost positive they're out there. There's a lot of really proof. But if you get close to a black hole, that one of our r-squared law I talked about means that if you get close enough, the front of your body is being accelerated or being pulled, the force on your front of your body is going to be much greater than the gravitational force in the back of your body. So it'll actually, it's terrible, but it'll blow you apart, right? In fact, a smaller effect like that is why there's tides on the Earth, and the fact that the moon pulls harder on one side of the Earth than the other, that has an effect on tides and things. And we cause tides on the moon. The reason the moon always faces toward us on the same side, you say, well, there's no water on the moon other than some like ice crystals, but not many of them. So how is it that what tides? Well, they're actually tides of the land. The solid rock has tides. It used to. Now the moon always faces the same way because the tidal forces, pushing around the surface of the crust of the moon. Actually, well, if you work it out, it turned out that the fact that there's a different force in the front of the back of the moon ultimately resulted in the moon not spinning around anymore relative to the Earth. So it always has the same face facing us through these sort of forces. Anyway, but if you're near the Earth's surface, these things don't happen. The gravitational force on my foot is per unit mass, right? Is the same as the gravitational force per unit mass up in my head. I'm not being pulled apart. I'm not near a black hole. I'm just near the Earth, And so the result is that you feel weightless. You don't feel any forces, but you're experiencing a force. So weightless doesn't mean you're not experiencing a force. This guy's experiencing a force. His free body diagram is this: downward force of gravity acting on him. But there's no upward force due to he's not feeling any force on the sole of his foot, right? As I'm feeling right now as I stand on the ground. The ground's not pushing back. Okay, so it's clear what's going on in that situation. I guess I already talked about this. When we calculate the acceleration someone experiences, because the force of gravity is mg, right? So if I got a small object and a big object, so big M, big mass, little mass, and you say, what's the force of gravity? Well, he gets a little mg for his force of gravity. He gets big mg, bigger force of gravity on him, right, than this little rock. But the acceleration that results, if this is the only force by Newton's second law, you'd say, F net equals ma, and I'd say, for this guy, it's, let's see, what is F net is, if it's projectile motion, this is the only force in the problem, it's just mg, and I'll make downward positive x direction just so I don't have to worry about the sign here. So mg is the acceleration, is the force, and that equals ma. Oh, okay, the mass is canceled. G equals a. Same thing over here. Newton's second law, F net equals big ma, right? And I'd say, okay, but then that is just equal to, capital mg equals capital ma. Oh yeah, the capital m's cancel. So that's why acceleration is the same for all objects. The forces are different, but Newton's second law says, bigger force, it results in the same acceleration because you got a bigger mass. So in the last minute here, we have 5 minutes in the last minute. Here we go. All right, so we no longer can afford to go to the moon. So what we do is we evacuate a chamber to simulate what it would be like if we took a field trip. Oh, someone stole the feather. Oh, there it is. So I got a coin and a feather. See a red feather? If I was smart, I'd use the handle back here instead of hurting my hand. Oh, it went fast that time. So it's supposed to, there it goes. So that's what's supposed to happen. The coin falls faster than the feather. But that's not because the force of gravity is different on these two objects, right? So this isn't evacuated yet. There's air in there. But sometimes, cyclists or motorists, if they get right behind you, right, they can save gas by getting behind you and avoid resistance, stuff like that. So that's kind of what's happening right here. The feather's getting behind the coin and it's benefiting from sort of being in the wake of the coin. But every once in a while we'll get a good clean there. That was a good one. Where the coin wasn't just drafting behind the coin. And when it falls down, the feather takes its time getting to the bottom, right? But the coin falls lickety split. And that's what gave Aristotle so many problems, right? He didn't have a pump, right? he wasn't able to evacuate. Get the feather. I want to suck the feather into the pump, so I'll put that down there, and then I'll do this right here. And all I'm going to do is just suck all the air out of this chamber, right? If I can find the on switch, that's the hard part of this demo. I'm very close. I know it's right in front of me. Oh, here it is. Oh, yeah. And we'll see how long it takes. Oh, yeah. So all I'm doing is I'm evacuating this chamber. This thing has a little scoop in it that grabs air really fast, and then as air makes its way down, oh my gosh, it doesn't usually explode. So I think we'll be all right. Oh, we're so close. It's one more half. This is like another 20 seconds. I think it'll be a good vacuum. There it goes. It sounds different now. It's running out of air. Right? It sounds like my car, to be honest. When it's running. All right. All right. I think that's probably pretty good. So I'll do that. Now let's see what happens. So now there's no air in here anymore, and the feather goes pretty quick, right? Does it look like it's working? Yeah, good. Yeah, no fooling around. Laws are for real. And it's true. The thing is, I was struck, when astronauts first went to the moon, right? They did this, the guy holds the feather in the rock and drops him, But the thing is, in some ways, it's not as impressive because on the moon, it's already so weird in the first place, right? And the acceleration of gravity is much less there, so the feather falls slowly. So what's weird about that is the rock's going slow. Wow, rock, really, it's messed up. Whereas here, we got the full strength of gravity, right? We've got 10 meters per second squared acceleration, but we have an object that normally has wind resistance. The coin has wind resistance too, that's comparable to the wind resistance that the feather experiences when you drop it out before we evacuate the chamber. But what happens then is that the force of gravity is overwhelming. Like for the coin, the force of gravity is much bigger than the force of wind resistance. So when you do Newton's second law, right? The net force is almost the same as what the force of gravity would have been on the coin. The wind resistance is negligible compared to the force of gravity. For the feather, the wind resistance is the same as the wind resistance force was on the coin, but the force of gravity is really tiny because the feather has very little mass. And as we saw, this law I wrote down here, the force of gravity on the feather is very small. So the result is that the net force, when you write down Newton's second law for the feather, when it's out in air, the net force on the feather is dominated by the wind resistance. That's why the feather immediately achieves what's called its terminal velocity. So if I jumped out of an airplane, right, and they're all imagining this now, if I did that, I would reach a terminal velocity of like, I don't know, 100 miles an hour, 150, 150 miles an hour, depending on what cool position I assume, right? But if you drop a feather, it achieves a terminal velocity right away. It's really slow because the force of gravity is tiny compared to the force of gravity on me, right? The force of gravity on the feather is tiny compared to the wind resistance. So it doesn't accelerate very long before it's just drifting at a constant velocity, right? It doesn't speed up. So that's good. I'm glad we got to the point. We covered all the projectile motion stuff. We got the beginning of sort of about forces. We'll do a lot about friction next time with one of my favorite demos of the class. We'll do with I think you'll enjoy that. And we'll do lots of careful studies of friction. And we'll talk about other types of forces. And we'll talk about internal forces. Anyway, have fun. See you next time.